Hello and welcome to Year 11 Physics Paper 1 Revision, Part 2 of a 3-video series with me, Mr. Duffy. In video 2, we're just going to be covering the whole topic of electricity and circuits. Now, at the end of the last video, we found out about generating electricity. Now we're going to see about the uses of electricity in our modern life, okay? Electricity is the modern world. You do need to know all about it, okay? So there are some maths equations, and if you are not sitting the exam in 2023, you will have to learn these equations off by heart, so we'll get plenty of practice at those. But what is electricity? Let's go through that first. There are three parts of an atom: protons, neutrons, and electrons. No prizes for guessing that electricity is made of electrons. Now I want you to picture a bucket with no electrons in it. Now 1, 2, 3, 4, how about 6.24 million trillion electrons? That is the basic unit of charge, and it is the coulomb, and that leads us on to our first equation. Q is equal to I times T. The coulomb charge flow is equal to current multiplied by time. What does this equation actually mean? Electrons are really tiny, so you need trillions of them to do any kind of work. So what is electrical current? It is electrons flowing in a wire or a circuit or a conductor. So current is measured in amps, and 1 amp is equal to 1 coulomb per second. 2 amps will be 2 coulombs per second. 3 amps will be 3 coulombs per second, and so on. So this equation links these all together with time. So here are some examples. Easy. Here's a bit of a rearranging, and you got to change from time 5 minutes to 300 seconds. That's where the extra marks go here. And here at the end, I have to divide from 60 to convert from seconds to minutes. Time conversions are very important. This is a 4-mark question. Here's a real-life GCSE question worth 4 marks. When I see 4 marks, I'm thinking about tricks, and 24 hours is the trick. Remember our converting time slides? Well, here's the marking scheme. And you can't do it without converting for time. Easy. 4 marks for that. Now, if you're not moving, you're not working. Now, I think it's time for me to get rid of my face so you can see the rest of the slides properly. So, here we go. If electrons are not moving, they are not working, okay? So, how do we get the electrons to move? Here is where our next thing, potential difference, comes in. Potential difference, or voltage as it used to be known, is inducing a positive and negative charge, or a potential difference, across the wire. Now, electrons are negatively charged. They will be attracted to the positive end of the battery. Now, a 1.5 volt battery is pretty small, so that will be used for like remote controls or, I don't know, clocks. But if you want to use some more powerful, you need a bigger battery. And here's a 6 volt battery, which is 4 times bigger than 1.5. That will make 4 times the current flow and be able to do 4 times the amount of work, okay? So you need a potential difference, and that will make the current flow. And that will be used for something like bright torches or more powerful devices. Here's a quick diagram of a battery. Just be aware of the naming conventions. The anode is the negative terminal, and the cathode is the positive terminal. It is the opposite to electrolysis in chemistry. So here are 2 different metals, and in the reactivity series, we can make a current flow with just 2 different metals. The larger the difference in reactivity, the larger the potential difference, the more current will flow. So, why is this coming up? Let's do something even if it's wrong. Well, here is something that I really hated about science, and really hated since I started studying electricity. In 1799, Alexander Volta, who the Volt is named after, developed the first electrical battery. That's around 100 years before they discovered what the electrons actually were. So they said the current flowed from positive to negative. We now know it flows from negative to positive, but they haven't changed the definition. We still say it flows from positive to negative, even though it's wrong. I find it ridiculous. They've confused students for years, but well, that's science. Okay, you have to go with the marking scheme, so you draw the current arrows coming out of the positive end of the battery and going to the negative end, even though in real life it's the opposite. Now, what is resistance? It is measured in ohms, and it is the ability of a material to stop or flow. The flow of electric current is kind of the opposite of potential difference. Potential difference makes current flow, resistance stops current flow. Resistance is the bad thing unless you're looking to heat something up, okay? So we don't like resistance, and if you ever see maybe a warning sign on your phone that starts bugging out, or your laptop's overheating, that's a sign of resistance and the wire is causing problems. Resistance is bad unless something is designed to heat up. So these are all connected with Ohm's law. Surprisingly, George Ohm is the guy who invented Ohm's law, and its voltage is equal to current times resistance. Although you start saying potential difference is equal to current times resistance, voltage has gone out of fashion, potential difference is in fashion. So here is a potential difference, that's the good thing. Here is a resistance, that's the bad thing, and they are connected in it by Ohm's law. Ohm's law says in English, if you double the potential difference, you will get double the current, directly proportional. Ohm's law says if you double the resistance, you will get half the current, inversely proportional. So this diagram kind of illustrates that the potential difference, the volt, is trying to make the current flow, while the resistance, the ohm, is stopping the current flowing. So here are some questions you might be asked on Ohm's law. Nice and easy, just look at the numbers, write the equation, plug them in, get the answer. Same thing, just rearranging, that's why it's 3 marks instead of 2. And here we have a trick. We have milliamps to amps, so I have to convert from 2 milliamps to 0.002 and to get the correct answer. Now, if you didn't do that, you'd only lose 1 mark, but these marks start to add up if you don't divide or multiply by 1,000. Now, here's a graph you're going to see later on called an IV graph, and this is an IV graph of a filament light bulb. Don't worry about that for now. All I want you to know about is determine the resistance of the filament lamp when the potential difference is at 1 volt. I locate 1 volt on the graph, circled in green. I draw an arrow up to 1 volt till it hits the line, and I get 0.08 amps as a current. That's why it's 4 marks. I have to use the graph. Then I just simply take my equation, rearrange it. The voltage is 1, given in the question. The current I found from the graph, and I get 12.5 ohms. That's 4 marks. Giving them away. Now, combining equations, a potential difference, I see voltage. Now, this one, I see coulombs, and I see milliseconds. I'm immediately thinking Q is equal to I times T, and then I'm seeing resistance and potential difference. I'm thinking V is equal to I times R. All that's missing is the current, but I also know that it's 5 marks, so there must be a trick in somewhere. 2 equations with a trick, and there is. If I can find the current, I'm sorted. So here's the answer to the question in full. Q is equal to I times T. Rearranging, notice I've changed the time to 0.004 seconds, not milliseconds, to get a current of 40 amps. Then I write out Ohm's law, rearrange it, and I get 120 ohms. That is 5 marks. Think how much you'd have to write in a long answer question for 5 marks, and you get that just for the maths. Okay, on to experiment 3, investigating resistance. It's basically the longer a length of wire, the more resistance in it, as the electrons have to collide with more and more atoms. So basically, it's directly proportional. If you double the length of wire, you should find that the resistance doubles. So here is a hypothetical situation with just 4 ions, and the resistance is 3 ohms. Now I double the length to 8, and the resistance also doubles to 6, because it's colliding with twice as many positive metal ions. That is resistance. Now, there is a such thing as an ammeter to measure the current. There is a such thing as a voltmeter to measure the potential difference. There is not a such thing as a resistometer to measure the resistance. So to calculate the resistance, you must use Ohm's law, rearrange it as in the box as follows. So you set up the apparatus like this with the ammeter in series and the voltmeter in parallel. You have a ruler with different the wires, so you don't have to chop up the wire into little bits. Just move the crocodile clips wherever it is. Start off at 1 centimeter and so on. So here is the full write up in detail. I mentioned the series and voltmeter in parallel. I'm going to say what I do at detail for 1 centimeter and then just repeat it for the others. I forgot to say measuring the current with an ammeter and potential difference with a voltmeter, so therefore I put that in text and then you calculate the resistance. So just pay attention and make sure you can learn the 6-mark write-up, and note at the bottom you should pause between repeats to allow the wire time to cool down to room temperature. So you need an element of safety in every write-up. The wire can get very hot, causing burns, so a low current should be used. That gets you an extra mark if you talk about safety in your write-up. But also validity. If the wire is not allowed to cool down between repeats, then the resistance of the wire will increase because of the temperature, making comparisons of length invalid. You must let it cool down between repeats. And if you do it right, you should get a graph that looks something like this. Directly proportional, a straight line through the origin 0, 0. Now, the cross-sectional area of a wire, this sounds fancy, it's just how wide or thin a wire is. A thin wire has a small cross-section, a wide wire has a thick cross-section. It's that basic. Now, the larger the cross-sectional area of a wire, the lower the resistance, as the electrons have more room to travel. They are inversely proportional, and that will lead to a graph like this. And overall, the summary is from left to right. If I change the metal, I will change the resistance. Different metals have different resistance. If I double the area, I will have half the resistance. It's inversely proportional. Or if I double the length, I will have twice the resistance. They are directly proportional. Now let's talk about the metals we use in making electricity, and in particular copper and gold. They're excellent conductors. Copper is mainly used in buildings and wirings because it's a good conductor. It's not very reactive, so it will stay there for ages, but mainly because it's cheap and it's easily available. Ideally, we could make our buildings from gold, but we just be too expensive. You will find gold in devices like iPhones and other laptops and stuff. The reason you'll find them in that is because you only need small quantities with very thin wires. If I had a copper wire in my iPhone, the battery would be dead before I pretty much left my house because the resistance is so much higher, okay? It'll just be really warm and a complete waste. That's why there's all these expensive metals in your technology devices, and you should recycle them because these are precious metals. And you get money as well. They knock money off your phone, so you might as well do it. Now we're on to circuits, okay? A circuit is, first of all, you have all these components, and you need to be able to draw each of these in your exam. They normally ask you to draw one, so you have to learn these off. So press pause and practice drawing these, definitely for sure. There are two types of circuit, series and parallel. A series circuit, all the components are in the same line. Here's two light bulbs in the same line. In the parallel circuit, they are in different what we call branches. And we're going to compare the two circuits now. A series circuit, all the components in the same line, whereas in a parallel circuit, the electricity, which is highlighted in green, can take different paths and different branches each time. Notice that it's coming out of the positive terminal and going to the negative. That's wrong, but we just got to stick with it. So here is a circuit set up with 3 cells, an ammeter, a variable resistor to control the current, and a light bulb. And I'm going to talk to you in detail about variable resistors because you use them every day. A variable resistor controls the current in a circuit. A low resistance equals a high current, and a high resistance equals a low current. Common sense. So for brightness control, we use it for that. That could be in your home. But I'd say you, as teenagers, mainly use it in your mobile phones. If you want to turn up the volume, you would decrease the resistance, and that will allow more electricity flow to your speaker, increasing the volume. If you want to turn down your screen brightness, maybe save battery, you would increase the resistance. That will dim your screen because less electricity is flowing to your screen. So let's talk about series circuits, and all the components are in the same line in a series circuit. Now, there's one of 6 things that you need to know. Potential difference in series circuits, current in series circuits, and resistance in series circuits, and then the same thing for parallel. So 6 things in total. Let's go. So potential difference in series circuits. First of all, you add up all the cells to get the source potential difference. That's your battery. Here we have a 6-volt battery. Here we have a 12-volt battery. And if you notice that the voltmeters are in parallel, these are identical components. The way I know they are identical is that they each get an equal share of the potential difference. 12 divided by 3 is 4. With non-identical components, they will get different potential differences, but they all will add up to 12. 8 plus 1 plus 3 is 12. Next, current in series circuits is easy. An ammeter will have the same reading no matter where it is placed. If it is placed at the top, it will be 0.31 also. Here's another example, 0.3. It's everywhere. The current is the same. And resistance is easy as well. You just add, literally just add. You will be giving these numbers in your exams. They don't expect you to know the resistance of a light bulb just by looking at it. They will tell you it. And in this case, I have 6 plus 6 plus 6 is 18. In this case, I have 6 plus 3 plus 7 is 16. You just add up the resistors, and the reason you add them up is because the electricity has no choice but to go through them when they are in series. So to sum up series circuits, you add up the batteries at the start, the cells, to get the source PD. The source PD is split amongst the components. If they are identical, it's split equally. If they're non-identical, non-equally. The current is the same, and you just add up the resistors. Now, the disadvantages of series circuits are many. Components cannot be turned on and off. The classic example is the Christmas tree lights. If one light breaks, they all break. All components get the same current, whether they want it or not. And finally, the more components added, the greater the resistance and the less potential difference in current they all get. So the light bulbs will get dimmer and dimmer and dimmer the more they add, whereas you'll see in a parallel circuit, they all stay the same brightness. So on to parallel circuits. A parallel circuit has different branches, and the main advantage is you can turn different things on and off. In this diagram, I can turn light bulb 2 off by opening the switch, but keep light bulb 1 and 3 on by keeping the circuits closed. So that allows me, for example, to turn on my dishwasher without turning on and off my lights. It's parallel circuits are all over your home. So here's a car. Now this car wants its lights on. It will want the window wipers on, but it mightn't want the heating on because it's a bit hot inside. This circuit will allow it to do it. Now the first thing about potential difference in parallel circuits is it's the same as the source potential difference. If the battery is 12 volts, they'll each get 12 volts. If it's 20 volts, they'll each get 20 volts. If it's 1,000,000 volts, they'll each get 1,000,000 volts. They all get the same potential difference. So here's another example. And here, current in parallel circuits. Now, this is probably the hardest of the 6. The current 0.2 comes out. Now, these are two identical components, so it's shared equally between them. They get 0.1 amps each. But here is another example with identical components. They get 0.1 amps each. And with non-identical components, the resistance is different in them, so they will get different amounts of current. So if you want to follow it from A1, it splits into branches A2, 3, and 4, and then A2, 3, and 4 combine back together to make A5. So 1 is equal to 5. So if we take a look at this real-life exam question, A2, well, if A3 reads 0.12, and so does A4, A2 will also, because they're identical, and the 3 of them will add up to 0.36. A1 is equal to A5. Non-identical components can get different amounts, but it would still add up to 0.3. If you add them 3 numbers up, it will add up to 0.3. Finally, resistance in parallel circuit is the easiest of them all. I don't really know precisely what it is, but all I can say is that it's less than 4. It's always lowest than the smallest number you can see. So this is less than 4. Here I see 200 ohms is the less of the resistance to be less than 200. Here I see we're into kilo ohms, so the resistance will be less than 1 kilo ohm or less than 1000 ohms. Why? Because the electrons just have more paths to follow. The more paths you add, the lower the resistance. Whereas in a series circuit, the more components you add, the higher the resistance, because the electricity has no choice but to go through them. So parallel circuits are far superior. This isn't on your course, but if you want to know the maths to why the resistance decreases, there you go. But here is the summary of parallel circuits. The potential difference is the same as the source, so all the light bulbs stay the same brightness. The current is split among branches, so each component gets the current it needs, not just the one current. And finally, the total resistance is less than the smallest resistance of an individual circuit. This sums it all up. And advantages of parallel circuits over series. Number one, all the components get the same potential difference, but you don't get something for nothing. Your battery will drain faster. Different components can be turned on and off. That's really a huge advantage. The total resistance is lower, and remember, resistance is the bad thing, so that is great. And each component gets the appropriate amount of current, not the same amount. It's all good with parallel circuits. So, explain how closing the switch would affect the current in the variable resistor. This question wasn't answered well. Here's the answer, okay? Well, if I close the switch, the electricity will follow the path of least resistance, and the switch has zero resistance at all. It's not designed to be a resistor, so the current, the reading on the ammeter will read zero, and there will be no current going to the variable resistor. So that's how it explains this answer here, if you want to spend a moment looking at that. Now, here's another question. The student concluded that the total number of resistors was inversely proportional to the total resistance. Explain why the student was correct. Use data from the graph. If it tells you to use data from the graph, you must. Now, you could pick 2 and 4, or I'm going to pick 3 and 6. So at 3, the resistance is 16, and then when it is doubled to 6, the resistance is half to 8. That is inversely proportional, and I've proved it mathematically. Here's another example. What is the potential difference across X? Well, it's a parallel circuit, so it's the same as the source PD, 6 volts. Calculate the resistance. Well, Ohm's law, 6 divided by 2 is 3 ohms. Nice and easy. Here's another thing about circuits. When the temperature of X increases, its resistance increases. Well, the potential difference stays the same. It's the same as the source, but if the resistance increases, the current will decrease in X, and that will decrease the total current in the circuit. Now, IV characteristics. What's all this about? IV characteristics is just a fancy name for resistance. Remember, resistance is just voltage divided by current, and that's an IV graph, okay? Now, you need to know about ohmic and non-ohmic conductors. I'll explain what it means. What does that mean? It means this. An ohmic conductor is a fancy name for a wire, or an ohmic resistor is a fancy name for a fixed resistor. Either way, they give you this shape of graph, and you need to know 3 IV graphs for your course. An ohmic conductor gives you a directly proportional graph. The shallower the line, the higher the resistance. The steeper the line, the lower the resistance, but they're all straight lines through the origin. Now, sometimes people get confused with the lines below the x-axis. It just means the current and potential difference are going in the opposite direction. It doesn't mean they're less than zero. For a filament bulb, you get this S shape that you might have seen earlier on, and the S shape is a result of this. So press pause for a moment and read through this. They get really hot, okay? For a light bulb to pump out the amount of photons it does, it gets up to 2,000 or 3,000 degrees. That's why they're filled with argon, not oxygen, or go on fire. But this greatly increases the resistance, and that results in an S-shaped IV graph. Explain how the resistance of a filament lamp changes as the potential difference increases. Here's your exam answer. The current increases, which causes the temperature to increase, which increases the resistance. That's a nice, easy 3-mark question. Final IV characteristic you need to know is the diode. The main thing to take from this is nothing goes below the x-axis, which means no current flows in the reverse direction. So how does a diode work? How does a diode ensure the current only flows in one direction? Well, as you can see at the top, the resistance is very low in the forward direction, 0.2 ohms, but very high in the backwards direction, 2 mega ohms. That's 2 million ohms. No currents flowing through 2 million ohms. So that's how a diode works. And so if you put your batteries in the wrong way, your remote control uses a light emitting diode, the current will not flow. That's why you have to put the batteries in the right way. So why would no electricity flow? There is no current in a diode. A diode has a very high resistance in the reverse direction. That's what you must say. Here's an example of a torch circle, which is correct. Again, it is technically wrong, but you say the electricity comes out of the positive end of the battery, so that is the correct one. Now, IV characteristics, that is experiment number 4, and it's pretty much identical to experiment number 3. You're just changing, instead of a length of a wire, you are changing the component. Okay, so look at the layout here, and you also include a variable resistor so you can change the current. So the overall setup is like this. I've got a power supply, I've got an ammeter in series, I've got a variable resistor to control the current, got the voltmeter in parallel, and then this time I've decided to use a filament bulb as my component, though I could use a motor, I could use various things, but I'm just choosing a filament bulb. So here's your write-up, and you need to play and pause and read through this. I've highlighted all the key things that you need to know. Okay, but the key is at the bottom we then change the current using the variable resistor, and then you measure the changing current and potential difference each time. You can then change the direction of the current to get the negative values by swapping around the wires at the battery, and you do the same thing, and then you'll just get these IV characteristics. Again, I explained that the negative current and potential values, how can they be less than 0? They're not, they're just going in a different direction, the backwards direction, giving you this shape graph. So again, for safety, the component could get very hot, the light bulb could get very hot, so a low current should be used. And it's the same thing again. For a valid comparison, the light bulb should be allowed to cool down between repeats, or else you will have more than one independent variable, making comparisons invalid. So here's a real-life question on this. How the current in a resistor, the constant, varied with time. It's a 6-mark write-up question, and that is just what we've done. Now on to automatic current control. A variable resistor we have to use ourselves. I have to press the volume up, I have to press the volume down, I have to change my screen brightness. This does it all automatically. Now for the LDR, that stands for light dependent resistor. The arrows indicate light. A thermistor has got a weird shape, I can't explain it. So a light dependent resistor has a very high resistance in the dark and a low resistance when it's bright. What would this be used for? Well, you could talk about automatic street lighting. Here's a circuit with an ammeter and a light dependent resistor. Now when it is dark, the current will be the current will be low as the resistance will be high. Below a certain level, a switch will be triggered, turning on the lights at night time. That's what you want. Now let's picture morning time. It's getting brighter and brighter and brighter. The resistance is getting lower and lower and lower. And what you see is this, is that the current increases. And if the current increases above a certain level, the switch is triggered to turn the lights off for daytime. And this time will change every morning by a couple of minutes as we go through the seasons. Thermistors are the high resistance when it's cold and a low resistance when it's hot. And remember to draw the symbol. They ask that quite a lot. So what uses might that be? Well, air conditioning. If it's cold, I don't want to get any colder, so I want a high resistance in my air conditioning unit. But when it's hot, I want a low resistance, so more electricity flows and the air gets cooler. This can also be used with automatic central heating, just in the reverse way, like the light dependent resistor. So that's the first chapter done on circuits. Now we're on to the second part, domestic electricity. And this is 3 chapters. Electricity in the home, it's all to do with safety, energy transfer, and the national grid. How we get electricity from the power station to our homes. So AC/DC, they're not a band. It means alternating current or direct current. Well, actually, they are a band as well, but well before your time, even well before my time, and I'm old. Okay, so you don't need to know the generator effect unless you're doing triple higher. But as you can see from this diagram, alternating current goes in both directions. Direct current only goes in one direction. So here's the graph, it going above and below the x-axis, whereas direct current does not. So direct current, you're mainly talking about batteries, really, low voltage devices. The current just flows in one direction. It's, batteries really. Alternating current, we're really talking about electricity generating in a big power station. So remember from the end of the previous video, to make electricity, you need to make a giant magnet spin. Here's a turbine turns the generator, which makes the electricity. Now, if you make a magnet spin, you are changing the potential difference every turn, okay? So that's why it's alternating. The potential difference changes, so the direction of the current changes. This is more triple higher stuff. I wouldn't worry too much about it if you're doing combined, okay? Now, so basically, to make a huge potential difference in a huge current, you're going to need a massive spinning magnet. So that's why you need a big power station. Alternating current, you need to remember these two numbers. The frequency is 50 hertz. That means the potential difference changes direction 50 times a second. And the potential difference is 230 volts. You need to remember that number. So domestic electricity, it's really all about safety. And here we are on to the plug. You need to know about a plug and how it keeps us safe. We use plugs every day. You need to know the wiring inside. So take a look here. You have a cable grip and an outer insulation. They'll be made of plastic or rubber. The casing of the plug itself will be made of plastic. Now you have 3 wires inside. The neutral wire completes the circuit. The live wire in brown, that is what actually carries the electricity, the current, and the earth wire grounds the charge for safety in case there's any metallic casing. You're going to see that in more detail in a minute. And a fuse is there in case too much electricity and a power surge comes in. The wire in the fuse will melt, stopping your device exploding. So here's an example here. As you can see, it's frayed, this charger wire. If it gets frayed, get a new one because you are now exposing yourself to the current. The insulator is gone. So if the live wire touches the surface of a device with a metallic casing, look at the toaster, metallic casing, microwave, metallic casing, the earth wire grounds the charge, preventing a dangerous buildup. So it can be used with metal cased appliances and it stops you getting electrocuted. Now, here's a question. Which one of these plugs is correctly wired? Now, I know the middle one is green and yellow. I remember that. So it's going to be B or D. And the neutral wire turns out to be blue. So that will be your answer there. It's answer D. So if we take a look here, that's why. I know the middle wire is going to be green and yellow. And that's why. Here it says the light fitting does not have an earth wire. It doesn't have an earth wire. Why is it still safe? Plastic, plastic, plastic. Plastic is an insulator, and you must say that's why it is safe. It is an insulator. Here's another example. State the color of the covering of the neutral wire and state which 2 parts are used for safety. Okay, well, firstly, blue is the color of the neutral wire. The earth wire and the fuse are used for safety, and double insulated means that the case is made of a plastic insulator. Do not say plastic coating. It's actually made of plastic. Now, what's wrong with this diagram? Well, I'm looking up top and I'm seeing that earth wire isn't connected and the cable grip as well. But this, being honest, in an exam and the pressure, I might have got this wrong, but it's only worth 2 marks, so I wouldn't worry too much about it. It's a real suggest higher level question. Fuses, how do they work? They have a thin wire inside. If the current gets too high, so 5 amp fuse, if the current gets above 5 amps, the wire will melt and it will stop the circuit completely. What's the point of fuses? Well, say electricity can be a bit volatile and you can get power surges. So say the same amount of electricity that turned a washing machine ended up going into my mobile phone would explode. So it just is a safety device that you can put into plugs. But it can only be used once. Once that wire has melted, you have to put in a new fuse. This is where circuit breakers come in. Circuit breakers, now in your home this is called a fuse box, even though it doesn't contain fuses, it contains circuit breakers. And the thing is, they can be used again and again and again. You don't need to know the electromagnetism unless you're doing triple. All you need to know is if the current gets too high, it pops out, breaking the circuit. And if you want to use it, you just push it back in. So what are the advantages of circuit breakers? They can be used repeatedly, they operate faster, they pop out straight away, whereas a fuse, melting the wire takes a little bit longer, so that will increase the risk of damage. So circuit breakers reduce the risk, but you can't put circuit breakers into plugs. That's a disadvantage. Now on to equation 19. Power is equal to potential difference times current. Okay, in plain English, if I increase the potential difference, I increase the power. If I increase the current, I increase the power. And it's used for comparing devices. Here are some of the maths that you're going to need to use. Easy. Rearranging for 3 marks. Easy. Bit of a trick here with the milliamps at the end, but still easy. Now, here's a 5 mark question. The mean power transfer is 5.75 watts. I'm seeing voltage, calculate the resistance. Well, the only thing I'm thinking in my head here is there's a trick and I don't know the current, okay? Current is key. If I can find out the current, that links those two equations together. So power is equal to voltage times current. Rearrange for that. And I get 0.025 amps. Then voltage is equal to current times resistance. Rearrange, I get 9,200 ohms is the resistance of the person. 9,200 ohms. 5 marks for that, not bad. Now here's another clearly inversely proportional diagram. The battery had a power output of 230 milliwatts. Seen a trick? Milliwatts. And 36 ohms. Determine the potential difference of the battery. Well, I'm going to locate 36 on my graph and I get 0.08 as my current. Then I just plug in the numbers, okay? Easy as that. 4 marks. Uses of electricity in our daily life. It is essential for the national grid. Now, if you live in a city, you probably won't be too familiar with these, but if you drive through the countryside, you'll see them all the time. Cables are easy. They're the big thick wires at the top. Pylons are the things that hold the cables. That kind of look like mini Eiffel Towers. So what is the national grid? You need to know its definition. A network of cables and pylons that transfer electricity from the power station to the consumer as efficiently as possible. Just one question they asked one year. The grid goes underground in towns and cities for practical reasons, but it makes maintenance much harder because you have to dig up the ground and the wires get a lot hotter because they're surrounded by insulating soil. Now these guys are real heroes, okay? Anytime there's a storm or a blackout, these are the guys that get the grid back up and running, and I think they deserve a lot more credit than they get. Here's a real life exam question. Calculate the mean energy transferred each second to 3 significant figures. And they even tell you what a year is in seconds. There you go. Nice and easy. Now transformers, okay? If you don't get the reference, again, you're too young. But this is were a big cartoon when I was growing up. Transformers, robots in disguise. Anyway, okay, a transformer is not a robot in this case. It is something which alternates the potential difference and current in the wires. You have a step-up transformer coming out of it, the power station, and a step down, and now we're going to look in detail at what both of these devices mean, okay? So, don't worry too much if you're doing combined about the structure. Again, don't worry if you're doing combined, but if you're doing triple, give it a quick read over. I'll be going over it again in my paper 2 paper. But anyhow, a step-up transformer. What is the point of these transformers? Okay, they use one of the key equations, something we've already done, and this equation tells us you can either transfer power at a high potential difference and a low current, or a low potential difference, or a high current. So here's a power station, and say this power station makes 600 megawatts of power. That's 600 million joules a second. I want to transfer that electricity to a consumer as efficiently as possible. So a step-up transformer uses this equation, and I'm going to show you mathematically what it does. So its purpose is to increase the potential difference so the current is decreased. This greatly reduces the amount of energy lost as heat in the miles and miles of cables. It increases the efficiency of power distribution. Here's the maths to prove it, okay? So let's have a look. First of all, the power station, P is equal to V times I, it generates 24,000 amps of current. That is a lot of current, which means a lot of heat will be lost as thermal energy in the cable. In order to reduce this from happening, we use a step-up transformer. A step-up transformer increases the potential difference to 400,000 volts. Looking at the maths, that reduces the current to 1500 amps, and that greatly reduces the heat loss through the cables and increases the efficiency. The electrons, they have lots more room to move through the cables, and the high potential difference means each individual electron carries a tremendous amount of power. It's very efficient. Low current equals less heat loss. Now, when I get to my town or city, I can't have 400,000 volts going round. That would literally be electricity leaping off the walls and killing people. So I need to reduce the potential difference to a safe level. Remember, it's 230 volts in the UK. This is where a step-down transformer comes in. Don't worry about its workings unless you're doing triple and it's more for paper 2. I'll focus on it then. But just quickly, what is the purpose of a step-down transformer? To decrease the potential difference to a safe level. So once the electricity reaches its consumers, they don't get electrocuted. That's it. Okay, so let's do the maths. A step-down transformer decreases the current to 230 volts and increases the current to over 2 million. And that's great because that can spread out to all the different flats, all the different houses. They all get a lot of electricity. It's exactly what you want. Lots of electricity at a safe potential difference. Just as a little aside, okay, 230 volts mightn't be enough for a factory. It might need a bit more. So instead of 400,000, it steps down to 33,000 and then to 230. So they can step down in several steps, just to be aware of that. So what do you need to be able to do? The top equation you don't need to know if you're doing combined. The second equation you do need to know if you are doing combined. Okay, so I'm going to focus on that one now. So a transformer has 230 volts and a current of 250,000 amps in its secondary. That's Vs and Is. The primary current was 20,000 amps. What is the primary voltage? Well, I write out my equation. I rearrange it for my primary voltage, plug in the numbers, and I get 2,875 volts as my answer. Here's another example. This time I'm looking for the current, IP, the primary current. So I rearrange for IP, plug in the numbers. Now there's a bit of scientific notation here. 4.2 mega amps means 4.2 by 10 to the 6 million amps, and also significant figures as well. Here's a real life exam question with easier numbers. An 18-volt battery could not be used. Well, that's because you need alternating current for transformers to work, and batteries give direct current. And calculate the output. Well, 18 times 2 is 36. Divide by 12 gives me 3 amps. You can do this very easily. Explain the advantages of transmitting electricity at a very high potential difference. Very low current, less thermal energy loss to the surroundings, increases the efficiency. That is from the marking scheme of a real exam. It's exactly what I've just said. Now onto this equation. Power is equal to I squared times resistance. They particularly like asking this on higher level papers because it involves the square root. Here's where it comes from mathematically combining these two equations. And here are some examples. Easy, more like what you'll get at a higher level question, but they'll probably ask you at a higher level to find the square root at the end. Easy marks though. Here's a real life question, and this is combining equations. I'm seeing 5 marks. Now first of all, I'm seeing time and the coulomb. That's Q is equal to I times T. Then I'm seeing power, watts, and resistance. That's P is equal to I times V. I need to find the current again, then I'm sorted. So look at my answer, it's very similar to before. Q is equal to I times T. Find out that I is 60 amps. P is equal to I squared times R. Plug all my numbers in and I get 3.83 ohms. 5 marks for that. Imagine how much you'd have to write to get 5 marks in a long answer question. Easy street. Now onto our final electricity equation. It's a nice easy one again. Energy is equal to the charge flow times the potential difference. Easy, easy, easy. Handing you marks. Remember C, coulomb, the unit of charge. Here's a trick with millivolts, but you're well used to your tricks by now. Basically, if you go through your whole exam paper without multiplying or dividing by 1,000, you've probably gone wrong. And that is the end of the combined section. Triple still have to do static electricity. Although combined students, it's still pretty interesting, and it's only another 2 or 3 minutes, so why not stick around? Okay, so that's domestic electricity done. On to static electricity. What is static electricity? Well, static means to be still or not moving. It is electricity that is not in wires. It is electricity that is in insulators. And the vast majority of things in the world, wood, plastic, concrete, cardboard, carpet, yourself, your clothes, are all insulators. Static electricity is pretty common, and there's only 2 chapters here. I'll go through them as quickly as I can. So static electricity is electricity that cannot flow easily as it is on an insulator. It is static. It is generally caused by the transfer of electrons by friction. I'm going to say that again, by friction, because it's so important, making one object negatively charged because it has gained electrons, and leaving the other positively charged because it has lost electrons. So for example, you need to be able to explain why the balloon sticks to the hair. They're both insulators. In this case, rubbing the balloon will make the balloon negatively charged. It will have gained electrons and it will be attracted to the positive charges in the girl's hair. Here's another example of a balloon sticking to a wall when it's rubbed. And here's a real extreme example of a Van der Graaf generator you've probably seen in school. You can do it yourself right now. If you've got a pen or a pencil, rub it in your jumper, get some little pieces of paper, and you'll be transferring electrons onto the pen, and it will pick up paper because opposite charges attract. Extreme case of static electricity will be lightning with massive friction between the clouds, resulting in a huge potential difference. When it can hop through the air, the potential difference is massive. So, can I outline how static electricity is formed? Here we have a polythene rod that's rubbed with a cloth. Electrons are transferred onto the cloth by friction, and if I hang the 2 rods together, they will repel each other because they are negatively charged. Just pause, and here's the answer as follows for 4 marks. They're transferred by friction, making them negative, and they will repel each other. You can also have a C-state. In a C-state, it's the opposite. It tends to lose its electrons and become positive, but the end result is the same. You have two positive rods. They will electrostatically repel each other. Sorry about my handwriting here, but you get the idea. So, have you ever noticed that you sometimes get these tiny little electric shocks from door handles or maybe a stairrail or something? Here's what's happening, okay? The student walks across a woolly carpet. Electrons are transferred by friction. A static charge builds up on the student. Now, here's the key point 4. There is a potential difference between the student, who is negative, and the door handle is positive. And when the student touches the metal door, all the electrons are discharged, causing a spark. The electrons are earthed. And here's the exact same thing from an exam, just as I said. Full marks for that. These sparks, though, a little spark in your finger, who cares? A spark with a load of petrol can cause an explosion, so you have to beware of safety in static electricity. So when a truck drives for ages, even though it may be metal, it's surrounded by insulating air, so the electrons will stay on it, and by friction, it will be dangerous once it goes for refueling. In order to prevent this, before refueling, a line is connected which earths the charge, and that makes it safe so there will be no sparks. Same thing with refueling airplanes, okay? You don't want them to explode on the tarmac, so this bonding cable is connected before refueling, and that will stop the charge. In fact, the refueling hose cannot be turned on until the bonding cable is connected, ensuring that there will be no explosion. So here's some exam questions based on static electricity. The student becomes negatively charged. Well, it's the transfer of electrons by friction, but you must say in what direction, from the carpet to the student for the second mark. Some carpets have thin copper wires running through them. Why will this make the student less likely to get a shock? Well, copper has a low resistance. It is a conductor, and that will mean there'll be no buildup of charge on the student. Here is an example of rubbing an acetate rod with a claw. You can see it becoming positive. Acetate becomes positive. Polythene becomes negative. And 4 marks for that question. That's not too bad. Just read through that. Neat. Here's another example, okay? You have a balance and you have a reading of a balance of 100.25. I put a plastic rod on top of the balance and the mass reading increases even though there's no mass. Explain why. Well, the reason is there is a downwards force in the balance because the rod is negatively charged and there is electrostatic repulsion between the rod and the balance, even though there's no mass on it. They also asked the balance had a 0 error. It should read 0 when there's nothing on it, but it reads 100. Normally 0 errors do matter, but in this case it doesn't matter because I'm just looking for the mass increase, so it doesn't matter. The difference is just the changing in reading. And finally, a negatively charged rod is held near an earthed conductor. Explain why a spark jumps between the negatively charged rod and the earthed conductor. You must say there is a large potential difference, causing electrons to move through the air from the rod to the conductor. An electrician, they are well used to electric shocks, I'm sure, in that job. The electrician would have received an electric shock unless the circuit was disconnected. Explain why. This one wire in the switch is live. If the circuit is not disconnected, it will have a wire at 230 volts. The electrician is earthed, so there's a large potential difference between the live wire and the electrician, resulting in an electric shock. Feel the force. We're nearly there. We're nearly finished. Okay, you can feel electrostatic repulsion and electrostatic attraction. It's kind of very similar to like magnets. When you put the two north sides of a magnet, they repel each other. The two south sides, they repel each other. But opposite charges attract, and it's kind of like the opposite poles of a magnet. It's very similar. Electrostatic repulsion is very similar to magnetic repulsion. You need to be able to draw these field diagrams. Just know that the arrows go outwards for a positive charge and inwards for a negative charge. Again, here's the same thing. And you need to know the strength of an electric field increases or decreases with distance. And here is electrostatic attraction. The field lines attracting each other, or repulsion, they're not allowing each other to go near. And here's a real life exam question with the field lines going outwards and direction of the particles, electrons, neutrons, and protons. So that's it. That's static electricity done, which means that topic 2 electricity is done, and that's video 2 all done as well. So thanks for sticking with me. Great to see you all, and I'll see you for the final video, video 3, which will be on the final 2 topics, which is the particle model, topic 3, then radioactivity, topic 4, and then there'll be exam technique at the end of that as well, so please stick around. So thanks for staying with me, and I'll see you for video 3. All the best.